Okay, so we want to talk about physics, right? So, and I mean, we want to talk about physics, right? We want to be able to have discussions about physics, because physics is a way in which we understand the natural world in a very particular, well-defined manner, such that mathematical modeling is an effective tool in a very specific way. And that's what I want to talk about in this first lecture today. So, let me ask you a basic question. How do I describe how far something is, or how long something is? And another associated basic question, how do I describe how long something takes, or how much time something takes, or, things like that. And so, well, I have these nice hand-drawn slides here. For whatever reason, I've decided that this is going to be part of my thing is that I like hand-drawn slides. It's going to be a thing I do. I'm also going to edit on things I do on PowerPoint and stuff onto the screen. And also I'll probably do possibly whiteboard at some point. But most likely, if I want to do like hand drawings, I'll draw it, in front of me and then hold it up, or I'll prepare it ahead of time. And if I want to like show you me drawing something in real time, I'll just show it on the screen with me completely out of the frame. I'm gonna see how that goes. I might also do a conventional whiteboard, but for now I have these hand-drawn slides, and I like them. I'm gonna go with that. So let's say you are commuting to work, right? And somebody asks, "Oh wow, that's obnoxious. You have to go to a job, and not only do you have to go to it, you have to sit in your car and drive. And depending on the circumstances, it might not be a very pleasant drive in order to get to that job." And it's like, man, well, how far is that? How long do you gotta sit there doing that? I'm lucky enough that when I was working at my most recent job at Sandia National Labs, my commute, I got to see the Sandia Mountains and the city of Albuquerque from the Sandia foothills every day. So it was actually a fairly pleasant part of my day. But if I was to describe, so I would actually be glad if that was not longer, but I don't know. I actually did take the sort of shorter route. The route that took a greater amount of time, but was shorter in distance and gave a much more pleasant view a great many times. And so, but maybe your commute is not so good. But anyways, we want to describe in a consistent way how far the commute is, right? Subjectively describing, what it's like is an important and interesting conversation. But we want to describe something simple and objective, which is what is the actual distance, right? So naturally, you would describe it in terms of a distance you already know, right? So we typically describe it in terms of things like well, I have right on here, like a mile, right? And if you're just familiar with the concept of, algebra, which that's all you'll need to follow along here, I will assume at least sort of high school algebra, but this is sort of intended to be like a college freshman level that will use calculus, but will not assume at the beginning you know any calculus. So we want to describe, x miles, where x is our variable there. So x is a number, but what's a number, right? So, you say, okay, it's some number of miles, right? And a mile already is something that we have to define, right? So we define distances in terms of distances that we all agree on, right? So one would be like, a sheet of paper, right? We could take, we all know that these sheets of paper are 8.5 by 11 inches, but we could take one of these arbitrarily and say, this is the standard now for 8.5 by 11. We lock it in a vault like they did with the meter stick, and say, okay, this is exactly 8.5 by 11. That's not how we define distances anymore. We have much more universal ways of defining things. But nevertheless, we do have to find something like that to define a distance or a time. And so then that behooves us to say, okay, well, if let's say I was describing things in terms of, instead of miles, in terms of paper. So this is one paper, this is two papers, and so on and so forth, right? And so, but then, okay, well, what if I want to describe a distance that's like 1.5 papers, right? Well, that's more complicated, right? So this is 2 papers worth of distance, which we all know, since these are 8.5 by 11, that's just 22 inches. But what if I wanted 20 inches, right? Or what if I wanted 12 inches or whatever? So it gets kind of ambiguous, right? So I want to just describe my commute, but it's not exactly, say, 5 miles, but it's not exactly, say, 6 miles. How far is it really, right? So obviously, the astute amongst you might be aware of these things called fractions and decimals that we use to describe, partial quantities, right? So we already have in mathematics a way of describing not a complete amount of a distance, right? We all agree on what a mile is. It's based on a certain number of feet, and foot is defined on some reference that was at some point the length of some stupid king's foot, right? And so now we all define 5,280 feet as the length of a mile. And then we describe, some number of miles. So then we say, okay, well, let's just describe, why don't we just... So that's basically the question you might ask then, right? Is instead of saying it's 5.5 miles, why don't I just say, okay, well, if miles are too coarse a resolution, right? If that's not specific enough, if that kind of is okay, it's, a certain number of miles, and let's say, okay, well, let's just go back to feet, right? Okay, so let's pull up the calculator here. Let's do 5280 times 5.5 is equal to 2,900 or 29,040 feet. Or sorry, just 29,040 feet. The and, remember, is reserved for decimal places. And so then you might ask the question, right, okay, well, that's all fine and good. But what if I knew better than that, right? What if I want to specify not just, exactly how far... Maybe it's not a question of, I want to show you that it's not exactly 5 or 6 miles because it's, not 15 to 20 minutes of commuting. It's a question of maybe now instead of the commute time, now we're trying to, measure the exact distance, right? Because we want to install some piece of infrastructure, right? And maybe it's a telecommunications array or something, right? Where we need to know the exact distance so that we can calculate all the losses on the signals and everything, right? And so, for whatever reason, right, knowing the exact distance in feet is not good enough, right? Because it's not exactly 29,040 feet, because it's not exactly 5.5 miles. Maybe it's 5.51 miles, right? How many decimal places do you want to use, right? Because of course now I could ultimately multiply this by 12 and get it in inches, and I could multiply that by 1,000 and get thousandths of inches. And then you might say, multiplying by 1,000, that sounds a whole lot easier. Why don't we use the metric system? And from here on out, that's mostly what we're going to do. But it is important to understand imperial units for several reasons. One is it reminds you that units are kind of arbitrary, right? We do have some amount of choice in what we use. In modern times, the metric system is generally, or strictly speaking, it's the SI units, System International, right? And it's a very well-defined thing with very broad universal standards based on things like transitions in the cesium atom that don't make reference to any particular physical object they just make use of the structure of chemical elements. Those things are themselves, the stability of chemical elements is based on a particular set of physical conditions. We'll talk about that way down the road. But generally speaking, the modern SI units are fairly universal, well-defined things. But we do ultimately have a choice in how we define things like the meter, right? We use these well-defined things like the cesium atom to define them, and we use these nice, well-defined number systems to define what's a meter and a kilometer, right? And it reminds you that, a kilometer is ultimately just 1,000 meters. But the nice thing about miles and inches is it reminds you, when you change distance scales, it actually kind of does change things a little bit, even if it's ultimately the same thing, and there's a very deep connection there to understand the metric system, but also to understand the anachronicity of imperial units there. But there's also a value in imperial units in that you could be tempted to think, therefore the meter is the length, right? But the meter is also arbitrarily chosen. It's arbitrarily chosen on much better footing than the actual foot. But nevertheless, the value of learning in imperial units is that you remember that they are kind of arbitrary, and so. So then maybe, eventually specifying in inches isn't good enough, and thousandths of an inch, or so if we're going to use the metric system, like I just, went on this whole thing about how that's what we're going to do, well, you're going to need to specify a certain number of decimal places then, right? Because now we can dispense with, feet and inches and all that, but we still have to deal with, we can just specify everything in meters and use decimal places to deal with our specificity. But then it's a question of how many digits after the decimal place do you want to use, right? And so there's sort of this thing here, right, where sorry, I had to change the order of my slide deck there to show these first. So basically, we all learn at some point that there's these different types of numbers, right? There's integers, there's basically integers like 1, 2, 3, 4, 5, 6. There's fractions, a half, a quarter, a third. I didn't put, other, and I did put down there other random fractions, 2/3, 5/7, whatever, all sorts of things. But these are all what's called discrete. Which means you can specify each number, right? You can write down a fraction and you're done writing it, right? Compared to if I have there's numbers like the square root of 2 that just you never will have the ability to specify them, right? Because these, what you can do is essentially you can always write down a fraction for a fraction, which is a tautology, but it's an important tautology, right? Versus a number like the square root of, right? So a number like a third, right? If you write it down as a decimal, you have to keep writing the number 3 over and over and over, but it's just the number 3 repeating, and so we know that, and so we just say, okay, it's a third, and we have this thing where we basically leave it unsimplified, and we leave the division problem left in our notation rather than specifying the decimal places, because we know, okay, it's just going to be 3 repeating forever, or whatever it is, and so then the thing is okay, what then? How do you deal with numbers like pi and the square root of 2, where there is no repeating pattern? So it turns out for dealing with numbers like the square root of 2 and numbers like pi are a little bit different. That's something we maybe get into later. But basically, numbers like the square root of 2, I can still tell you, you know what a square root is, you know what the number 2 is, you can take the square root of 2, go through this procedure, and you get this irrational thing. Pi, you probably don't really, unless you know how to do clever things with Taylor series and trig functions, or if you know some other clever tricks, you probably don't know how to actually calculate pi, right? You have to do it through this, some sort of empirical way. And so there's a subtlety there. But in both cases, you kind of understand, right? It's how specific do you want to be? How many numbers after the decimal place, right? Is it 5.5 miles that I have to commute? Is it 5.512837796? Is it 5.51927386598329435? Hopefully I repeated the decimals correctly there, but I probably didn't. But those are both arbitrary numbers. But you get the idea, right? There's a question of how specific do you want to be, and then there's a question of what does that mean, right? Because you can basically imagine here's all the numbers between 0 and 1, right? And you can imagine that, okay, well now each of these sort of lines below is zooming in a little bit further. I'm sorry, my handwriting is so abysmal. So the next one down is let's look at, okay, so you can see here 0, 1, 2, and all these little tick marks showing the different decimal or fractional numbers in between. And then down here you see just between is just between 0.45 and 0.55. Very poor handwriting, and I didn't put the 0 point, I just put point. So it looks like a negative, but that's 0.45 and 0.55. And so then it's the same number of tick marks all over again, right? So you can just zoom in, and then you zoom in again, and this is 0.499, and this is 0.5001, right? And then there's even more, and then there's even more tick marks, right? And so it's like where do you stop? And it's not clear, right? And so in mathematics, it turns out that that's actually a very deep question, right? Where do you stop your specificity? And of course, the answer is and there's questions about what happens when you never stop your specificity, and if you know things about Cantor's arguments about cardinality of sets. But in physics, this manifests in a particularly interesting thing that they thought about in ancient Greece called Zeno's paradox, right? So if you ever heard this story about Zeno, Zeno's came up with this paradox about the story about Achilles, right? The famous warrior, a very athletic person that could go super fast. And so it's a question of like, okay, imagine that Achilles is in this tortoise and a hare scenario, right? Where Achilles starts out behind and the tortoise starts out ahead, right? So it's like, okay, how does Achilles catch up, right? Because in order to catch up to the tortoise, first he has to get halfway to the tortoise. But to get halfway to the tortoise, he has to get a quarter of the way to the tortoise. And to get a quarter of the way to the tortoise, he has to get an eighth of the way to the tortoise, and so on and so on and so forth. And so a question now is, obviously those of us living in the real world say, well, that's ridiculous. He just starts moving and he doesn't actually stop when he gets halfway there, does he? Right? And he doesn't stop when he gets a quarter of the way there either. He just keeps going, right? And we describe it as him being a halfway there or a quarter of the way there, right? The paradox doesn't come from reality, or reality itself would collapse, and I think you can all tell empirically reality exists and does not collapse on a daily basis. And so, but there's something there about the way we describe reality, isn't there? Where our specificity has to have a limit to it, or you basically like run into this problem of infinite computation time, right? Because that's what it is. This is not a problem of infinite time spent actually running in the world. It's a question of infinite computational time, which you may see my poster of Alan Turing. If you're thinking about the Church-Turing thesis and computability and finite computing times, you're getting ahead of yourself. But you have some interesting ideas that we can discuss in the comments section. Shameless like, share, subscribe. Etc. etc. So that's the sort of thing I want to explore, is stuff like that. And I'll start doing some more quantitative mathematical examples as we start describing physical quantities mathematically in more detail. But for now, I want to leave you this thought of paradoxes that come not from reality being paradoxical, but from our descriptions being this sort of strange thing that it's like Richard Feynman said, it's the unreasonable effectiveness in mathematics in descriptions of nature in terms of physical law. And it's unreasonably effective in some level because we're so good at dealing with these paradoxes, right? We have this awareness of paradox, and as a result, we're able to do things that boggle the mind. The mathematical tools that we have to understand nature these days, really these days meaning since the 19th century, or really since the 17th century when Newton did his thing. But then you sometimes run into these paradoxes where it's like, well, how could he ever overtake the tortoise? And the answer is that he never stops, right? Because nothing ever stops, right? Because counting is a lie, because no two things are identical, because there is no such thing as a thing. There is only such a thing as stuff and periodic boundary conditions. What are periodic boundary conditions? That's a tale for another time. Thanks for watching.